Besides the mathematical nature of the universe and besides the animal communication and human communication, God illustrates His communicating power in what I call the language of life. We're now going to focus on that. The language of life revolves around or focuses on this issue of DNA. But before I can really address the issue of the language of life, I need to dispose of a problem. In our society, there seems to be some belief in something I call the DNA myth, and I want to dispel that myth. The myth is that DNA contains all the information necessary to build an organism. This can be seen in, I guess for you, what's the age-old, the very old film Jurassic Park, where you're supposedly you find some DNA in a fossil mosquito that had taken DNA out of a dinosaur, and they extract that DNA and they reconstruct a dinosaur. As if we knew how to do it, you could take the information on DNA and actually reconstruct an entire organism. There is a sense in which many people believe that all the information necessary to build an organism is found in the DNA. That, however, is what I call the DNA myth. That is not true. Evidence that DNA does not contain all the information for life is seen in a variety of ways. One, sperm, when it fertilizes the egg, actually provides, when it does so, only its DNA. So thinking of a sperm when it contacts an egg, what happens is it opens up, dumps out its DNA. Nothing else of the sperm gets into the egg in the process. The consequence of that is that as the fertilized egg develops into an adult, all the cell components, the nucleus, the endoplasmic reticulum, the Golgi bodies, all those things we learned about as organelles in the cell, did not come from the father, they come from the mother. Those things, so all of your endoplasmic reticulum, membranes, cytoskeleton, all that stuff doesn't come from your father at all. It comes entirely from your mother. There's information that only comes through the mother, and information that doesn't come from DNA. It's in the cell itself. In fact, mitochondria have their own DNA separate from the DNA of the nucleus, what we usually think of as our DNA. So, and in the process of development, as the cells divide, some of the cells become the head of the organism, some become the tail or the backbone of the organism, the legs of the organism. What determines the head end versus the other end is determined by cells, not the DNA. But the cells, the cell components outside the nucleus, they're not coming from the DNA, they're coming from the mother. So that's one of the reasons that we believe that not all the information needed to build an organism actually comes from DNA. A further indication, if you take frog eggs that have been fertilized and carefully, it's kind of hard to do, but if you carefully take out the nuclei of the frog eggs, that means there's no DNA left in the eggs, those frog eggs will continue to divide from 1 cell to 2 cells to 4 cells and so on, up to 10 times to thousands of cells, actually many more thousands of cells, without ever knowing that they don't have DNA, before they finally die and can't do this any further. So it appears that DNA is not required to do something like reproduce a cell, or at least divide a cell. And in fact, it takes a number of such divisions can occur before the DNA is in fact accessed. A third indication that DNA is not all that's involved in building an organism is the role of microbes in organisms' growth, in our growth. And as we develop from a single cell, there's a point at which our intestines are developing. Well, we need a gut flora in our intestines in order to help us digest things. That gut flora is introduced in the womb. And that gut flora is essential for not just our digestion, but it appears, the more we learn about this, that gut flora is essential for the proper development of the intestines. So it appears, and it's only the beginning of the story, I suspect that there's a lot more going on, that microorganisms are playing a very important key role in the development of organisms, in the development of humans, and that without them, an organism can't properly develop. If that's the case, then not all the information necessary for building a human being, for example, is in the DNA of humans. Part of the information is in the microbes, the microorganisms that in fact are in the human as the human is developing. A fourth indication or suggestion that DNA is not all that's involved comes in the form of identical twins. When you encounter an identical twin pair, this is a situation where the two individuals developed ultimately from one egg being fertilized by one sperm. Once that fertilization occurred, the cell divides into two, the two into four. If at any point before they divide the next time into 8, if those cells get separated in any way, if the two cells get separated from each other, for example, then each of those cells can potentially develop into a final adult human being. And if that happens, they have the same DNA, because there was only one fertilization event that actually generated the original cell, and that DNA was duplicated into the two cells. So once you separate the cells, they now have exactly the same DNA. They develop into what we know of as identical twins. Identical twins with the same DNA, though, are not identical. I'm sure you probably have met some identical twins. You're familiar with them. You realize that they each have different personalities. There can be other differences between the identical twins that indicate that something besides DNA must be involved, because if DNA was all that was involved, they would end up absolutely identical in all ways. Furthermore, we have the indication in Scripture that humans have a non-physical dimension to them. They have a soul and spirit. We also learn in Scripture that animals have a soul. And it's most likely that that has nothing to do with the DNA. Whatever a soul is, whatever a spirit is, it's something that is not controlled by or determined by or made by the DNA. So not everything that is human, not everything that is animal, is in fact created by the DNA. And so it's even possible that the soul that we're going to say is created by God, that the soul may actually contribute to the development of a human. The soul may contribute to the development of an animal, in which case the DNA certainly wouldn't have everything to do with building an organism. So the evidence is that not everything in an organism is in fact determined by the DNA. So the claim that DNA contains everything necessary to build an organism is, I would argue, a myth. Well, if that's true, how much is in fact determined by the DNA? Well, the answer is we don't really know for sure how much of the information necessary to build an organism is in fact residing in the DNA. What we do know for sure, we don't know how much in a maximum sense, but we have at least the idea of the minimum amount that is necessary in DNA to make organisms is in the building of proteins. Putting it one way, the DNA contains a recipe manual, a recipe book, for the construction of the proteins that an animal needs or a plant needs. We know that DNA does at least that much. It probably does a lot more than that, almost certainly does a lot more than that, but at the very least, it's a recipe book for building macromolecules, specifically the macromolecules of proteins. And the instructions for building a protein, the little individual recipes, are in fact called genes. The genes that code for give us information for a recipe. Those things are called genes, but genes only make up 2% of the length of at least human DNA. What is the other 98% doing? We don't really know at this point. We got some clues, we got some hints, but we don't know for sure. Perhaps I'm guessing DNA probably contains the recipes for all the macromolecules of an organism, but we only know for sure about the proteins. It may even have a lot more functions, but at this point, we don't know what those are. What I want to do at this point, however, is begin to look at DNA. It certainly has the potential, the power, the ability to store a lot of information. So what is it about DNA that allows it to store so much information? DNA, as we've already seen, is a nucleic acid that is made of a monomer known as a nucleotide. There are for DNA 4 nucleotides: guanine, cytosine, thymine, adenine. We sometimes refer to them just by their first letters, C, G, T, A. And basically DNA is a string of nucleotides. That's all it is. Stick one nucleotide in, and then another one, and then another one, and another one in a long line. At each point along the DNA, you have 4 choices about what you can stick in at that particular point. 4 different nucleotides are possible. You can put either a C or a G or a T or an A in that particular position. Given that, if you're reading this thing, or you let each nucleotide represent something, each position, if you considered only one nucleotide, you could only code for 4 possibilities. Like, for example, in this illustration, I'm putting different colors on them. Red, blue, green, yellow. And we're representing 4 different colors. They can represent 4 different things. But that's not carrying a lot of information. 4 choices. But what if we considered 2 adjacent nucleotides together, 2 at a time? As we went along the chain of nucleotides, we looked not just 1 at a time, but considered 2 adjacent to one another. In that case, the first one could be a red, and the second one could be either a red or a blue or a green or yellow. So there are 4 possibilities if the first one is a red. There are 4 more possibilities if the first one is a green. There are 4 more possibilities if it's blue. There are 4 more possibilities if it's yellow. So we actually have 16 possible combinations of nucleotides, if the order makes sense to you. You could have the red-red, the red-blue, the red-green, the red-yellow, and so on for 16 possibilities. So if you looked at 2 nucleotides at a time, you could code for 16 different things there. But it turns out that if you're going to code for proteins, proteins are made from amino acids, and there are 20 amino acids. So 16 possibilities isn't quite enough to code for all of the different amino acids. But what if we in fact considered 3 nucleotides in a row? In that particular case, for each one of the 16 that we considered, looking at only 2, we'd have 4 possible combinations for the third one. So we'd have 16 times 4, or 64 possible color combinations if we looked at 3 at a time. 64 possibilities allows us to code for up to 64 things. So we could assign, let's say, one of the amino acids to be a red-red-red, another amino acid to be a red-blue-red, another amino acid could be indicated by a red-green-red, another by a red-yellow-red, and so on. We could code for our 20 amino acids and still have 44 different things left over that we could code for. Like, let's say, begin reading the DNA here, or end reading the DNA here. We could put periods into the and we could code for other things. So 64 possibilities allows us to code for quite a wide variety of things, and all that it requires is to look at 3 nucleotides at a time. And in fact, in the real world, in DNA, that's exactly what happens. 3 nucleotides are read at a time. 3 nucleotides are called a codon. Each of the codons codes for a particular amino acid, so we can code for our 20 amino acids. And so a sequence of codons, 3 nucleotides at a time, can be used to give a sequence of amino acids to build a protein. Now, since DNA has 3.5 billion nucleotides, we've got a lot of codons possibility. We've got more than 1 billion codons we can put into DNA. That's a lot. We can put a lot of information into the DNA. In fact, if we, let's say, took the English language and coded it into our codons so that maybe red, red, red is an A, and red, yellow, red is a B, and so on. We could code all 26 letters of the English alphabet. We could code another one. That's going to be 26. We got 64 possibilities, so we can have room for more. We can code for spaces, commas, semicolons, exclamation points, open parentheses, close parentheses. We can code for all of the characters that you might use in the English language. And then we could code, let's say for your textbook, we could code all the information of your textbook and put it into the DNA. We have enough room in the DNA to code for 1,200 of your textbooks. DNA is so long that even though you're using 3 nucleotides for each character, you've got enough length in that DNA to code for a tremendous amount of information. This is a special design of DNA that allows for an incredible amount of storage of information, which is absolutely essential, a key feature of DNA, the storing of genetic information. DNA is not only well designed for storing information, DNA is extremely well designed for copying information. So now we'll turn to that issue of DNA. As part of the design of DNA, it's the fact that DNA is so long in a string that you can store a lot of information, but DNA is not just a long string of nucleotides, it's actually a double string. So for every string of nucleotides, you have another string that's actually attached to it. And so you have 2 parallel side-by-side strings making DNA a double-stranded molecule. It's this double-stranded molecule characteristic that allows us to copy very effectively, along with 2 rules. If we have the double-stranded DNA plus 2 simple rules, we can create copies very readily. And the rule is that adenine, the A, always pairs in the second strand with a thymine, a T. So A goes with T, and guanine always pairs with cytosine. So C goes with G. So let's say we have a strand of nucleotides here, and we start over here at this end. The first one here is a thymine. So the rule is adenine pairs with thymine, so an A should go with that T. The next one's an A, so the T should go with it. Next one is a C, so there should be a G that goes with it. With the G, there should be a C, then we need an A, then we need a G, then we need a T, a G, an A, a G, and a CCC, and a T, and a C, and a G, and a G, and a T. We can then, based on one strand, produce a second strand very readily. By the way, the rate at which I did it, if that's the way the cell did it, we would die, because we need to do this. Millions of these things need to be paired per second for DNA to be copied effectively. This is the basic rule on how to copy, and this is what makes DNA so very easy to copy information. So for example, for us to make a copy of the entire DNA molecule, we start with our double-stranded DNA, and the first thing we do is we unzip the 2 strands, separating them from each other. Then we make a copy of each strand. So we combine our A's with T's, C's with G's. We do this on one strand. We do this simultaneously on the other strand. And at the end of this process, we will end up with two double strands that are identical to one another. And so if you compare these two here, you've got one strand here that looks exactly like this one. T's and A's, T's and A's. They are two identical strands made in this particular fashion. It's also possible to just copy a portion of the DNA, because remember, DNA's function, among other things, is to have recipes for proteins. Let's say you only want one recipe. You only want to make a copy of a portion of the DNA. Well, we can do that too. And what we do there is just unzip a portion of the DNA. Then we make a copy of that portion that we unzipped. And then we take that copy, take it out of the DNA, out of the nucleus of the cell, and make our protein with it. And then we rezip the DNA. Now, I might add that there's actually a step here I haven't mentioned, which has to do with the fact that DNA is not only double-stranded, but it's also twisted, and so it's spiraled. So actually, the very first thing we need to do is untwist it, then we unzip it, then we copy it, then we rezip it, then we twist it back again. All of these things are done with extreme speed. The spinning and the unspinning actually occurs at millions of revolutions per second. It starts at various places along the DNA, and it comes together somehow without twisting and breaking the DNA, which is an amazing design. And then there's a molecule that runs along and unzips it at a very fast pace. There's another molecule that comes along and makes the proper connections of A's with T's, C's with G's, all the way along, and does so at millions of nucleotides per second, so that we can copy the entire DNA or copy individual segments of the DNA in only minutes of time. But this very simple set of rules, this very simple design of a double strand with simple rules, A's with T's, C's with G's, allows us to copy DNA very efficiently, very quickly, and actually with very few mistakes, making an amazing design.